I'm glad to be in Singapore again. So I would like to start by motivation of by motivating the problem of different scales that involve any fundamental theory that tries to describe at the same time particle physics and cosmology. And these are some of the main scales that enter in the physics. Somewhere here is the electroweak scale, and perhaps physics beyond the standard model, which perhaps will appear in the TV scale or in the multi-TV scale. And then we have observations from cosmology which point out dark energy. The dark energy, if it is a cosmological constant, it doesn't change. It in principle defines two types of scales, two different scales. One is a classical one, because the cosmological constant has the dimensions of length -2, and can be inferred from the observations from dark energy and using the Hubble parameter. And it turns out to be 10 to the 26 meters, which is essentially the size of the observable universe. While a different way is to associate a scale is to associate it to the dark energy, to the energy density, in which one uses the Planck constant and h bar to define a scale. And this is length to the -4, which is enabling Lagrangian density. And in that case, this scale is much different than this one. It's much smaller. It's about 85 micrometers. And this is the one that I used here. Put it into energy units is milli-electron volt. Then we have, of course, the quantum gravity scale, and somewhere in between there is the inflation, which describes another approximate accelerated expansion with another value of the cosmological constant. And it can be anywhere. Okay, it depends on when we will measure the tensor fluctuations where it will be. So, as I said, there is a challenge for any fundamental theory to be able to explain, describe the physics around the scales. In principle, there are two possibilities. It could be that the physics is independent. In other words, besides every scale, there is a different physics, and somehow the theory should accommodate them. But I think the most interesting possibility is that there are connections between them. There are some examples. For instance, one can use the Higgs field to make inflation, or in models in low-scale gravity, Planck scale is emergent, and so on. Here, what I will discuss is a possibility to connect the inflation scale with supersymmetry breaking scale, assuming that supersymmetry is not far from the electroweak scale. And at the same time, I will just assume that there is vacuum energy that could be accommodated by the theory. So this is what I was trying to do recently, and I will discuss it in this talk. So since I'm going to talk about supersymmetry, I would like to start with the main problems of implementing inflational models in supergravity, in the framework of supergravity, so that we can understand what's going on, how to address this problem. I would say the most serious problem is to satisfy the slow roll conditions by a general potential that comes from the supergravity, and in particular what is called the eta problem, the eta parameter, which is one of the two slow roll parameters that enter inflation, which is given by the second derivative of the potential divided with the potential, normalized with the potential at the horizon crossing. This is in supergravity, the potential is expressed in terms of two functions of chiral superfields, such as the inflaton, because in supergravity, the inflaton should belong to a supersymmetry multiplet, which is a chiral superfield. In other words, it comes together with a fermion and another scalar, which becomes complex. And it is the scalar potential is given in terms of two functions: the scalar potential, which is a real function of the chiral superfield of the inflaton, say, which I call x, and a superpotential, which is an analytic function. And the reason that we take functions is because gravity is a non-normalizable theory. So in principle, in supergravity, one has a coupling constant, which is a Planck constant, and therefore one should consider non-polynomial interactions up to two derivatives, of course. And this is a formula that is valid for a general two-derivative supergravity. So D is a covariant derivative under Kähler transformations, and it takes this form. It's a derivative plus the derivative of Kähler potential times W. Now, the Kähler potential essentially determines the kinetic terms through its second derivative. And one sees, because of this exponential of k factors, so my units here is the Planck unit, so I would say put it equal to 1 to simplify the formulas. One sees that if it takes a second derivative, both derivatives can hit the exponent here, k. And therefore, we'll find an expression which is proportional to the potential itself times the second derivative of the Kähler potential. And when we divide by v, we will find the second derivative of the Kähler potential. Now, for a field which is canonically normalized, in other words, that its kinetic term is just unity, then k is just quadratic. K is xx bar. Therefore, if we take second derivative, we will find just 1 plus extra terms, of course, which come from the different pieces. So this is the eta problem, that there is this contribution, which is 1, which is big, plus extra contributions, which should be arranged in a way to cancel this 1 and then find something small. So that is the eta problem. Actually, there is a class of models in supergravity that have non-trivial Kähler potential, not of this form, which solve this problem, which address this issue that eta is not 1. And one class of them is the so-called no-scale models, for which what happens is that if you consider, let's say, take a scalar field like the inflaton or something else, which I call T here, just to differentiate the two, and assume that the superpotential is independent of this, but therefore the derivative with respect to this field of the superpotential, the explicit derivative vanishes. So one can find the Kähler potential in a way that one can cancel this 3 contribution here, which comes from gravity, from the first term, and one finds 0, even if the superpotential is not 0, which means that supersymmetry is broken. So these are the no-scale models, which typically for one field have this scalar potential minus 3 of log of t plus t bar, which has exactly the form that their contribution to the scalar potential vanishes. These models can address the eta problem. However, what happens in that case is that the resulting models, in general, suffer from another problem, which is a problem of initial conditions, that one has to start with values of the fields, of the field of the inflaton, which is trans-Planckian, in other words, bigger than the Planck scale, in order to make inflation work. And this, of course, breaks down the validity of the effective field theory, because once we consider trans-Planckian expectation values for the field, even if the kinetic terms are small, since you consider non-polynomial interactions, then there are all sorts of corrections, and the effective description of the models, the inflation models, break down. So that's a second problem. A third problem has to do with the pseudoscalar companion of the inflaton. As I said, the inflaton should belong to a chiral superfield, so it becomes complex, and therefore it has a pseudoscalar partner if the inflaton is scalar, the other way around. Now, this partner is another field which should not play any role in inflation. Therefore, it should stabilize. So it should acquire a mass which do not influence the physics of inflation. So that is a third problem. And then there are many others that come from the particular theory that one uses of quantum gravity, such as, for instance, string theory, which contains many other fields that need also stabilization, like the moduli, the problem to construct a de Sitter vacuum in supergravity and the string theory, and so on. So these are the list of problems that one has when you try to implement inflation in supergravity. I would like to give an example of all this, of how these problems appear in a particular setup of supergravity inflation, which is basically based on the Starobinsky model. So I just remind you that the Starobinsky model of inflation consists of adding the scalar to the scalar curvature a term which is proportional to the curvature square with some coupling alpha, dimensionless. This brings, this doesn't violate unitarity, but it brings an extra scalar degree of freedom in the metric, which can be easily seen by linearizing this term, introducing a Lagrange multiplier, phi, whose equation of motion is given by the scalar curvature. So it is given in this way. But then one can rescale the metric to put it, to cast it in a form which has a canonical Einstein term. And by rescaling the metric, one generates kinetic term for the scalar plus a particular potential. So this scalar can be, in Starobinsky inflation can be identified with the inflaton. And the scalar and the potential has this particular exponential form in Planck units, where m is the scale of inflation, which is related to this coupling, again in Planck units. And this model, it's a phenomenological model, which apparently, we know it fits well the experimental data. So in this context, one can just take this model and supersymmetrize it if you want to make it to go to supergravity. Then one has, the first technical problem that one has is, as I said, this scalar, once you supersymmetrize it, this scalar, which is the inflaton, will be complex, and therefore we'll need to introduce, instead of introducing a scalar Lagrange multiplier in this approach, we should introduce a chiral field, which is Lagrange multiplier. However, it is not so simple, and the reason is that in supersymmetry, the scalar curvature is a chiral superfield, and the scalar component, it's what is called an upper component. In other words, it's a superfield which appears in a higher component in the expansion in the fermionic coordinates of supersymmetry. And therefore, if you write R square, where R is the chiral superfield, this superfield does not contain the term scalar curvature square, because it's an F term. It's like the superpotential. So I need to write a D term, which is RR bar, in order to be able to supersymmetrize this term. And therefore, when one tries to linearize it, one has to introduce two chiral multiplets. One chiral multiplet is not sufficient. So in general, you have four scalar fields, scalars, pseudoscalars, two chiral multiplets. And this is the result. So I call these chiral multiplets T and C. They have the model has this scalar potential, which is of no scale type. So we see here that okay, once we supersymmetrize a model that works, that it doesn't suffer from that in which you can satisfy the slow roll conditions, then necessarily obtains a non-canonical kinetic term, which is of no scale type. In other words, if the superpotential is constant, then and you plug the scalar potential back in the supergravity expression for the scalar potential, you find 0. However, there is also a superpotential which has two pieces, one which is linear in this field C, which is the second chiral superfield, and another term which is quadratic between C and T, and it can be thought as a Dirac mass, like supersymmetrization of a Dirac mass. It's a Fermi, of course, it's supersymmetric. In this model, what happens is that T, the one field contains the inflaton, so the real part of T can be identified with e to phi, with some exponent, where phi was the auxiliary, the scalar of Starobinsky model, whose equation of motion was given by the curvature. And of course, contains an imaginary part, which is an axion type field. And then there is this additional chiral superfield C. And it turns out that this field is unstable during inflation. Actually, C appears linearly in the superpotential, which means that its F auxiliary component, which is the derivative of the superpotential, is constant, and therefore C breaks supersymmetry. In other words, C is the goldstino superfield, which contains the Goldstone fermion of supersymmetry breaking, which is called goldstino. So, as it is, the supersymmetric extension of this model does not solve the problem, and it is not a good inflation model. And one has to do something to depart from this in order to stabilize this field. There have been several proposals of modifications. For instance, one can modify the kinetic term by this way, and so on. And there is a effective field theory description of this class of models that can stabilize this extra field and provide models of inflation which are of Starobinsky type by essentially identify. The observation is that you can identify this C, this extra field, with a goldstino superfield. And therefore, any such model that stabilizes the extra field generates a mass for the scalar component of this field, which is the partner of the goldstino. And one can integrate it out because it is massive at the time of inflation. And one can obtain an effective field theory in which this C is an effective goldstino superfield. In other words, the supersymmetry becomes nonlinearly realized because the scalar component is integrated out. So this can be thought as a generalization of nonlinear signal models in supersymmetry. This integrates the procedure of integrating out the scalar pattern of the goldstino can be done with a constraint, like in nonlinear signal model. This constraint for supersymmetry is a simply can be shown to be x squared equals 0, where x is the Goldstino superfield. And this constraint essentially eliminates the scalar component of the scalar component of the Goldstino superfield in terms of the fermion. So the scalar component, it becomes a fermion bilinear, and this fermion is a Goldstino. F is the auxiliary field whose expectation value must be constant. So that's the solution of the general solution of the constraint. And the auxiliary field F is determined when you write the Lagrangian. So for instance, the Volkov-Akulov action can be written in this way very simply as a kinetic term plus a linear superpotential, which is the most general Lagrangian that you can write down with two derivatives, given the constraint x squared equals 0. Any other power is 0. Notice that this theory has also an arc symmetry, under which the fermionic coordinates have charge 1, the Goldstino has charge 1, and this superfield has charge 2. So the Volkov-Akulov action has an arc symmetry. So using this effect, this first of all, this action can be coupled to supergravity. Because of the constraint, the Kähler potential can take any form is similar, is equivalent to xx bar because x squared is 0. And the superpotential, in addition to the linear term, one can contain also a constant piece, which is in principle allowed. And now, which I call W0. And now the scalar potential becomes a constant. There is no scalar field since it was integrated out. The scalar Goldstino was integrated out. And this constant, the interesting thing is that this constant can have any sign, positive, negative, or 0. In global supersymmetry, it has to be positive in order to supersymmetry to be broken. But in supergravity, you have this negative contribution from the superpotential, which comes from this constant. It comes from gravity and can have any sign. In particular, when W0 is 3F, then the scalar potential vanishes, and then W0 is just the gravitino mass. Of course, arc symmetry is broken by this W0. Now, this gives an extension, a minimal extension of the R-squared gravity and the Starobinsky model. And going back to this term, to the expression that I said before, one replaces C by the Goldstino superfield, which satisfies the constraint, which is nilpotent. So I write it here. So the superpotential has a linear term, a quadratic term, and then a constant, which is, we tune it so that the minimum is at 0. And now this model has two fields. One is the inflaton, which has exactly the same form as the model of R-squared, Starobinsky. And then there is an axion, a pseudoscalar, which has a mass. And if you compare the masses, then one finds that the mass of the axion is much bigger than the mass of the inflaton at the time of inflation because of this exponential factor. And therefore, it doesn't play a role during inflation. So this model solves three of the problems that I mentioned before, the eta problem, the axion, and the stabilization of the axion. However, it suffers from the problem of initial conditions because one needs to start with initial values, which is trans-Planckian for phi, because of this in Planck units, in order to have successful inflation. So this means that if you start from trans-Planckian initial conditions for phi, there is no reason why the effective model of supergravity should restrict in this form, and one cannot write extra corrections in T which would invalidate these properties. Moreover, notice that this model provides a framework of connecting inflation with supersymmetry breaking. However, still the inflaton lives in T, while the goldstino lives in X, which are separate, although within the formalism they are connected. In particular, this model contains two scales. One is the inflation scale, M, which appears here, which was related to the coefficient of R squared. And another term is the coefficient of the linear term, F, which is related to the supersymmetry breaking. So there are two different scales which are separate and which enter in this way in that theory. So I think this example illustrates what I want to say. Now I can go on. So what we would like to do now is to find a direct connection between the supersymmetry breaking scale and the inflation by identifying the inflaton with a partner of the goldstino instead of integrating it out as we did before. In other words, we would like to find a framework, some models in which the inflaton is exactly the partner of the goldstino and does not suffer from this from the problem of initial conditions. So to do this, we will need an extra symmetry, which is an R symmetry, which is gauged. Now, this gauged R symmetry, the R symmetry implies that the superpotential is linear. There is no corrections because the superpotential must have the charge and charge 2, so we can associate, as I said before, also the X has a charge 2, and therefore there are no other. There is no way to the R symmetry protects the superpotential to have other corrections, and it implies to be only linear. In addition, we will gauge it, and there are two consequences of this gauging. The first is that by gauging the R symmetry, what will happen is that the pseudoscalar component partner of the inflaton will be absorbed by the U1 and to become massive, and therefore the theory will have only one physical scalar, which will be the inflaton, the partner of the goldstino. We will not have any other scalar. And the second consequence of having a gauge in R symmetry is that the potential will have two contributions. One which is called F contribution, which comes from the superpotential, and the second contribution which can come from D terms, from the fact that you have a gauge symmetry. And in principle, they could come with different signs, because the D term contribution is always positive, while the F term can be negative. So you can tune the cosmological constant at the minimum. Observation is that when the superpotential is linear, then the eta problem is automatically solved. In other words, the second derivative of the contribution of this superpotential in the second derivative of the potential is proportional to is zero. Okay, so to lowest order. So the reason is the following: that for linear superpotential, you remember I said before I described the eta problem, which comes from the second derivative of this exponential factor. There is another contribution that comes from this linear superpotential, which comes precisely with opposite sign. So at the end, the scalar potential is of the order of x to the 4, and therefore eta is 0. So this solves in a natural way the eta problem. And this is not no scale type, because the scalar potential will be canonical. So we will ask inflation to arise around the maximum of the scalar potential, so that we have small field deflation of the hilltop type, so that there are no large field initial conditions. And I described already the use of the gauging of the R symmetry. Now, in general, there are two types of models one can imagine, which I call case 1 and case 2, which are distinguished with what happens to the R symmetry around the maximum of the potential where you have inflation. There are two possibilities. The first is that R symmetry is restored at the origin, at the maximum. And another possibility is that R symmetry is spontaneously broken anywhere, and it is restored only at infinity. Here I will describe just the first case. In order to, we'll try to make a phenomenological model in which the superpotential is linear. The Keller potential starts with a canonical term plus a quadratic correction, which should have a small coefficient so that the expansion is the perturbative expansion is valid, and should require to have a maximum at the origin, which implies that this coefficient should be positive. So there are as I said, two contributions. One which comes from the F term, from the superpotential is proportional to F, and the other comes from a D term because of the R symmetry, and X has a charge under the R symmetry Q. And therefore, there are three parameters: the scale of the F term, the charge, or the scale of the D term, and the parameter A. And we'll assume that inflation happens around the maximum. So these are the slow roll conditions, which can be expressed in an expansion in, I call rho the module of X, which since occurs around the maximum, around the origin, then I can make an expansion around rho equals 0. And express epsilon eta in terms of this, and one finds that epsilon is of the order of is equal to eta square rho square to the lowest order, which means it's much smaller than eta. And here x is just the ratio of small x is a ratio of the charge over the f of the f term, so that the relative strength between the d term and the f term. Actually, the D term does not play any much contribution for inflation. One can consider X to be practically very small, and therefore the eta becomes small, and therefore epsilon becomes also small, just by considering that A, which is a correction to the Keller's potential, is less than 1, so 1/10, let's say. So inflation starts with the initial conditions near the maximum and ends when eta is 1. And this is the expression for the number of infolding, which is given by this interesting formula. It's 1 over eta times the logarithm of the ratio between the end and the initial value of the inflaton. We can write the expressions for the amplitude of the density perturbations, the scalar, the spectral index, and the tensor to scalar ratio. One can fit two of the parameters from the first two, from the amplitude and the spectral index, and then obtain a prediction for the tensor to scalar ratio. One sees that since epsilon is much smaller than eta, then one can neglect epsilon. Eta is fixed by the spectral index to be minus 0.02. And this is interesting because put it back in the expression of the number of e-folds. One has 1 over eta, so 1 over 0.02, one finds 50. So one finds already the right ballpark for the number of e-folds. And then one has the two parameters, the scale of inflation, the epsilon, which one can play. I mean, principally, they are independent parameters by fitting the amplitude of density perturbations, which gives a R which is small, smaller than 10 to the minus 4, and a scale of inflation which is less than 10 to the 12 GeV. So this shows that without making much of tuning, this formally gives a nice description of inflation in which one can solve the problems that I mentioned before. The next question would be, what about the minimum? If there is, of course, the inflaton starts at the maximum, as I said, of the potential, and then it goes down to a minimum, and this minimum should describe the present vacuum of the universe. So it should have a small cosmological constant, and it should break the supersymmetry in the way that we would like. An interesting possibility is to study whether this minimum can be studied also in a perturbative expansion around origin. In other words, if it happens for small values of rho. Because, of course, if it happens far, then this minimum is independent. It is model dependent. We cannot make much predictions. So the question is whether, as I said, we can describe this minimum nearby with almost zero vacuum energy. And the answer is yes, in a weaker sense, in which the perturbative expansion is valid for the Keller potential, but not for the slow-roll parameters. In other words, one has important corrections for the slow-roll parameters. One has to redo to evaluate the results of the inflation. For the generic potential, which is not fine-tuned, one obtains this range of values of the parameters. So since my time is over, I don't have time to describe the second possibility, and I go to the conclusions. So I remind you that I started with the motivated challenge of scales. There are several scales in a theory that tries to describe at the same time cosmology and particle physics. And here I described a mechanism. I tried to relate the scale of supersymmetry breaking with the scale of inflation by identifying the inflaton with the partner of the goldstino. And I described a framework in which this can be done. Thank you.
Thank you. We have time for a couple of questions. Yes, please.
What is the physical mechanism to set the initial condition of the inflaton at the top of the hill?
There is no particular mechanism. It has to be.
There is a problem.
There is a problem of initial condition. It has to start, of course, near the
Right.
maximum, and this maximum has a plateau to stand in place.
Yes, you have used some particular forms of the Keller potential, no, to reach these results.
Sorry.
You have reached some particular forms of the Keller potential
Yeah, this
to reach
forms,
the results. So there is some ambiguity, no, in the final result.
Yeah, I will tell you. The problem is not the particular form, but how to generate the extra correction. I mean, the Keller potential that I assume is canonical plus an extra correction. So there is the question whether there is a microscopic theory in which you can generate this correction, which has the right sign to create a maximum. This is something that can be done. I mean, we are in the process of doing it.
So you are saying that, sorry, you are saying that there is some ambiguity in the correction that you introduce?
The value.
Yeah.
Yeah, here it is. We start with canonical Keller potential, which is standard form, plus this correction. So
Yeah.
the question is whether you can generate this correction by macroscopic theory. And the answer is yes. I have examples, but it's ongoing.
Okay. Thank you.
Thank you. A brief question.
You may remember that I discussed some years back here an illustration that asymmetry is the sister of symmetry. And it looks to me that the seeking, like SUSY, a symmetry to stabilize something which generates masses of scales is simply wrong. We need the asymmetry.
What do you
And
mean
I
asymmetry?
don't- Yeah, it is symmetrizing higher symmetries are completely vanishing, even in this way of proceeding. They have no meaning at all.
We don't know.
Asymmetries.
I think that you should discuss it during
Okay.
the coffee break. Because
Okay,
I think that it's a rather complicated issue. And probably you have different opinion. Okay, I think we should move on. Let's thank again Ignatius for the talk.